Let us start today's discussion. Now, at the beginning of today's class, first of all, I'll go through an example problem for single slope ADC. The single slope ADC and dual slope ADC was discussed in our last class. So I hope that you remember how the single slope ADC operates. So after going through one example problem, I'll discuss two types of digital to analog converter circuits. And with that, I'll conclude our discussions on different types of data converters. Now, for this particular example, you know that the ramp generator, it is basically an integrated circuit. It is supposed to be associated with a resistor and a capacitor. So for this particular problem, let's say the value of the resistor is 100 ohms and the value of the capacitor is 17 nanofarad. The clock pulse that is provided to the counter, let's say its frequency is 1 megahertz. So its time period should be just the reciprocal of this, so 1 microsecond, or you can say 10 to the power minus 6 seconds. For the counter, for this example, let's assume the counter is a 3-bit counter. And using these values that are available to us, we want to measure input analog voltage up to a maximum limit of 5 volts. So this is the maximum limit of the input voltage up to which we want to measure. So in order to obtain that, what should be the value of the reference voltage to this ramp generator? So what should be the value of the reference voltage that we need to determine in this particular problem? So before proceeding further, let me write down two formulas of the conversion time for the single slope ADC that was discussed in our last class. So the conversion time, the time required to convert a particular analog signal into its analogous digital form, we represented it as T1 in our previous lecture, and the relation was in terms of the input voltage, the reference voltage, and the values of R and C. So here the reference voltage is the quantity that we need to determine. So let us write it in terms of the reference voltage. Okay, so using this formula, we have to determine the reference voltage. Now, for that, the values of R and C is already known to us. Now, what should be the value of V in and T1 that we should consider? For T1, the conversion time, another relation was shown in terms of the period of the clock pulse multiplied by small n. So what was a small n representing?
Number of counts, the counter count.
Yes, the number of counts the counter raises its count within the duration of t1, or you can say that the number of clock pulses that the counter receives within the duration of t1. Okay, so to further proceed with this problem, the next thing that we need to do is to determine the quantization interval, because our maximum limit is up to 5 volts, and for a 3-bit counter we would have 2 to the power 3 or 8 different quantization states. So what is the quantization interval between the states? That is the first thing that we need to determine. So for this case, that would be 5 volts divided by 8, which would equal to 0.625 volts. So that is the quantization interval. So in terms of the quantization interval, we can define the ranges of these 8 quantization states. For example, from 0 up to 0.625 volts, this would correspond to the binary sequence of 000. Then suppose from 0.625 up to 1.25, this would represent 001, 1.25 to 1.875, 010. In this way, up to 111, the range of the analog voltage that would give a 111 output. You'll find that it is 4.375 to 5 volts. So these are the different ranges of the analog voltage for which we are going to get a corresponding uh, or the same uh, digital output sequence. Okay, so in determining the reference voltage, we can consider any one of the sequence or any one of the quantized state and proceed uh, by determining what should be the value of T1 and V in for that particular quantization state. So for this first state, the counter is, suppose it is reset, it is not showing anything. So when it receives the first pulse, it is going to show 000. Upon receiving the second clock pulse, it is going to show 001. Then when it receives 3 clock pulses, it will show 010. In this way, up to it will receive up to 8 clock pulses when it shows 111. So for if we consider the first case, the first quantization state or 000, the counter is receiving 1 pulse or it is counting once. What should be the value of T1 for that case? Did you get my point? What I am asking?
No, no, sir.
I'm saying that consider the first quantization state. So for 000, the counter is receiving 1 pulse when it is providing you 000. If it is receiving 1 pulse, which means that it is counting once. Okay, then what can you say about small n? What is the value of small n then?
One.
Definitely
One.
1. So if the value of small n is 1, according to this relation, what should be the value of T1?
1 microsecond.
1
7
microsecond.
into
7 into why 7?
uh, number of clock pulses will receive.
Number of for the first quantization state, it is receiving only 1 clock pulse, right?
It's 1 microsecond.
So 1 into the period of the clock pulse, that would actually give you 1 microsecond. So that is your duration of T1 for the first quantization state. Now, corresponding to T1, what should be the maximum limit of your input voltage? That is this one, 0.625. So for this duration of T1 or 1 microsecond, the maximum limit of the input voltage is 0.625. So this is your V in corresponding to T1 equals 1 microsecond. So if you put these two values in this relation, which is 0.625 and 1 microsecond, and the values of resistance and capacitance that you already have, you will find the reference voltage to be 1.0625 volts. So that would be your corresponding reference voltage. Now, let's say that instead of considering the first quantization state, let us consider this third one. So upon receiving 3 clock pulses, the counter is going to give you 0, 1, 0, and the number of small n, or value of small n in this case would be 3, because the counter is receiving 3 pulses. So the value of t1 would be, in this case, 3 into 1 microsecond, or 3 microsecond. And the maximum limit of the or the maximum range of the input voltage for the third quantization state is 1.875. So for the third quantization state, you can use 1.875 as the value of your V in, and if you use these two values, put them into this equation, then again you will find that the reference voltage is the same reference voltage you are going to get. So no matter which quantization state you choose, ultimately you will end up with the same reference voltage. Now, in terms of graphical representation, so in our previous class we showed a graph something like this, that we have a straight line, the straight line that is produced by the ramped generator, and we had, let's say, a constant line that represents our input voltage. So for the first quantization state, when we define that our range is from 0 to 0.625 and corresponding digital output should be 000, which means that for this quantization state we have to provide one clock pulse. So let's say this is our 0 volts, this is our 0.625 volts. So within this period, the counter will receive one complete clock pulse. Okay, so this is the maximum range of the input voltage for the first quantization state. So for the input voltage, the value of the input voltage between this 0 to 0.625, for any values of the input voltage between this range will actually result in 000. For example, suppose if we consider the next quantization state, if we consider the next quantization state, so for that our ramp voltage is supposed to rise from 0.625 up to 1.25 volts. So within that period of time, another clock pulse is supposed to be passed for the second count. So from 0 to 1.25, this amount of voltage, 2 clock pulses will be passed to the counter. So any voltage that is in between this range from 0.625 up to 1.25, the counter will give the sequence of 0 1, sorry, 0 0 1, and for any voltage within this range the counter will give you 0 0 0, and in this way it will proceed further. So finally, it can be said that the uh, different quantization states are often represented by this sort of an staircase wave shape where 0 okay 000 represents 0 volts, 001 represents, suppose for this case, 0.625 volts, then 010 represented by 0.25 up to 1.875. Okay, in this way uh, the different quantization states and their corresponding intervals can be also represented in terms of a staircase diagram. So regarding this particular example, if you have any question you can ask. Otherwise, I move towards the discussion on digital to analog converter.
Sir, I have a question in dual slope ADC.
Okay, you can ask your question.
Can you go to the slide, sir, for dual slope?
This one?
Yes, sir. Yes, sir. Sir, here I understood the positive slope part, but I don't understand why the negative slope part starts from V in. Shouldn't it have been start from the baseline 0?
Is no, because for example, this is your output voltage, right? VB that we have along the y-axis.
Yes, sir.
So when your integrator is integrating the input voltage, okay, so it is continuously having the supply of this input voltage, and depending upon the flow of current, this capacitor is getting charged, right?
Yes, sir.
So when the capacitor is getting charged, the voltage across it is supposed to be getting stored across the capacitor. Now, when the switch is changing its position from V in to V reference, you are not clearing the voltage or discharging the capacitor, right?
I understood, sir. Thank
So
you,
the
sir.
capacitor voltage was already stored up to the point it was raised. So from there, it gradually decreases according to the slope.
Understood, sir.
Okay. Okay, regarding this example, you are not asking any question. I don't know how many of you remember previous classes discussion, or whether you have gone through that or not. But as the session is getting recorded, later on try to go through the example so that it becomes clear to you. Because here I consider that V reference is the unknown quantity. So maybe during exam, some of the other parameters maybe will be given to you in order to determine the value of that particular parameter. So if you understand this particular example, I think it would be quite easy for you to solve a particular problem. And also the operation of single slope ADC and dual slope ADC is quite similar. So a similar type of problem, if it is given in terms of dual slope ADC, I think it would be also possible for you to solve that as well. So try to practice the problem, or try to understand it later on. If you if
These
you
are from MMS Anand book, right?
the diagrams are actually from MMS Anand's book. Okay. Now the example is not directly from MMS Anand. Okay, but in MMS Anand book, I think you can find one example that might be relatable to the topic, but this is in general example to give you an overall idea about uh, about all the parameters. Okay, maybe in the MMS Anand book example, they haven't provided the information how to calculate the reference voltage or how to consider the different quantum states. So for that, I would recommend you to refer to this lecture. Then I think it would be much more clearer to you.
Okay, sir.
And for this topic, you can, for single slope or dual slope ADC, you can also refer to the book of David A. Bell. Okay, let me check the article number. So the article number from David A. Bell is 5.5. You can also refer to that. So I think if you consider both the books, the MMS Anand and the David A. Bell, you can have a better idea along with the lecture which was given in the last class.
Okay, sir.
Now for digital to analog conversion. So in today's lecture, I'm going to introduce two types of digital to analog converter. The first one is weighted resistor DA converter, and the second one is R to R ladder DA converter. So let us discuss the first one, the weighted resistor DA converter. Maybe you have studied in one of your courses, maybe even in the digital logic course. Maybe this was introduced. I don't know whether it was introduced or not, but let us quickly go through its operation. So before I start the discussion, I think from the circuit diagram, you can suggest which type of circuit is this one. So we are using an op-amp which is having an inverting feedback. So for this particular inverting feedback circuit, what is this sort of circuit in general called? Can you recall?
Summing
Summing amplifier.
amplifier.
Sorry.
Summing amplifier.
Summing am-
Yeah. So it can be called as a summing amplifier, or you can also call it as inverting adder as well. Because at the output side, you are supposed to get summation of the voltage drops across all these branches. So in that sense, this sort of a circuit is often referred to an inverting adder, and it can also amplify the output voltage depending upon the values of the feedback resistance and the input resistance of all the different branches. So in general, it can be an summing amplifier. So this inverting adder or summing amplifier circuit is going to be used as digital to analog converter with some conditions being imposed upon the values of the resistances. So the values of the resistances, you can see that they are in weighted proportion. So they are increasing proportionally from one branch to another. And this is an example of a 4-bit binary weighted resistor digital to analog converter. So each branch is actually representing one particular bit of the digital signal. So the first branch here, as you can see, it is denoted as the MSB, and the last branch here is denoted as the LSB. So for example, for a 4-bit digital to analog converter, the maximum or the final bit sequence is suppose 1 1 1 1. If you want to convert it into an equivalent analog voltage, you should give more weightage to which bits, the MSB or LSB.
MSB.
Obviously the MSB should get the higher weightage while the conversion is done. So the values of the different registers are that's why chosen in weighted proportion so that more weight can be given to MSB while providing an equivalent analog signal. The purpose of the switches is to represent the two possible states of a bit, either 0 or 1. So you can easily suggest that if the switch is closed, suppose if this switch is closed, this input a reference voltage is actually going to be causing some current to flow this through this branch. You can say that that is actually representing our binary bit 1. And if the switch is open, then even if there is the reference voltage over here, this path will be open, so no current will flow. So for that instant, it can be said that this corresponding branch is representing the binary bit 0. And that is same for all the other branches as well. So the switch is actually indicating the state of the bit, whether it is 0 or 1, depending upon whether the switch is open or closed. So if you consider this particular node, then the current flowing outwards of this node, which is represented here as II, is going to be equal to the summation of all these 4 currents, which is shown over here. Now, for an inverting feedback circuit where the non-inverting terminal is connected to ground or zero potential, from the concept of virtual ground, what can you say about the potential at the inverting terminal?
0.
So the potential at the inverting terminal should also be 0. So if the potential at the inverting terminal is 0, from here you can write an expression for the output voltage, which is very straightforward. That is 0 minus V out is equal to RF into IF. And here you can rewrite V out as minus RF into IF. That is written over here. Now, there is no current flowing. I mean, this current IF that is not going to flow through these two terminals of the op-amp. I mean, the inverting terminal or the non-inverting terminal. So no component of the current is going to pass through these two terminals. So the entire current is going to flow through the feedback resistor IF. So this feedback current is actually going to be equal to I, and it is equal to the summation of the currents flowing through all these 4 branches. Now these currents I1, I2, I3, I4, we can easily represent these currents with respect to the reference voltage VR. So the potential at this node is actually 0 volts. So for I1, we can easily write the expression to be VR divided by twice R. Now, whether there is going to be current flow or not, that is going to be depending upon the status of the switch. If the switch is closed, the current will be flowing. If the switch is open, current will not be flowing. So that is also representing our binary bit. So for this particular branch, let's say B1 is representing our MSB. So along with this expression of VR divided by twice R, we are going to multiply it with the status of this bit B1. So if B1 is 1, then this amount of current is supposed to flow. If B1 is equal to 0, then no current is supposed to flow. Similarly for the other bits as well, suppose this is B2, this is B3, this is B4. Okay, sorry. So for I2, we can easily write it as VR divided by 4R into B2. In this way, for the rest of the uh, two branch currents as well, we can represent in terms of the voltage register and the status of the bit. So if we replace all these currents in terms of their voltage and corresponding resistance, and put that value, that expression over here. So VR divided by twice RB1, VR divided by 4RB2, then here VR divided by 8R B3. In this way, if we put that expression instead of IF, finally we will end up with this pattern. And if the common term R is factored out from the denominator, this will be eventually our final expression. Following this expression, we can determine particular output voltage. So suppose for a binary sequence of 1 0 0 1, so this is for an n-bit case, but for a 4-bit case, suppose for 1 0 0 1, we can put the value of the bits, the reference voltage, and the values of the resistance, and we can determine the corresponding analog output voltage. Now if you look to this expression, you can see that the coefficient is along with each bit is decreasing in a proportional manner. So the coefficient with the MSB is the highest, and the coefficient with the subsequent bits are proportionally decreasing. So for the second bit, it is 2 to the power minus 2. For the third bit, it was supposed to be 2 to the power minus 3. In this way, up to n number of bits, which is 2 to the power minus n. So we are giving the lowest weightage to the LSB and the highest weightage to the MSB. In this way, this particular circuit is going to convert a particular bit sequence into its equivalent analog output voltage. Now, regarding some disadvantages of the binary weighted DAC, one disadvantage is that for n number of inputs or n number of bits in the digital input, you require n number of binary weighted register values. Now, for this particular design, the n different binary registers are supposed to be having a value which is quite precise and accurate, so that they are in equal weighted proportion. If there is too much error in the values of the resistance, then the ratio between two branches will change, and ultimately the final converted output voltage is not going to be giving an accurate result. So one thing that is mentioned over here, so each register is supposed to be having some amount of error. So but that has to be very minimum for designing this particular type of a circuit. So the error in each register must be less than the smallest register value. So suppose you are designing a weighted resistor DAC. Suppose you are having the first resistance to be 1 ohms, the second one is supposed to be then 2 ohms, the third one 4, 8, 16, 32. In this way, the values of the resistance is going to increase with the number of bits. So for example, if for this 32 ohm resistance, if the possible absolute error in the resistance is suppose plus minus 2 ohms, then the possible error is actually even more than or equal to the first two resistances. So that is going to be giving significant error in the calculation of the output voltage. So for this particular design, the resistance has to be very precise and accurate, having very minimum error in them. So manufacturing resistances with that much accuracy is often challenging. So the task, uh, uh, I mean, results in more manufacturing expense for this particular type of DSCs. Another thing you might have seen while doing different experiments in your lab is that maybe you are having a 10 ohm 1 ohm resistance or 10 ohm resistance very easily available to you. But if you want to take twice the value of these resistances, in the labs often what you do, you connect two 1 ohm resistances in series to get a 2 ohm resistance, or two 10 ohm resistance in series to get a 20 ohm resistance. Why that is normally done? Because uh, in commercially available resistances, it is difficult to manufacture a resistance that is going to be having a value of exactly 2 ohms. So the commercially available resistance, maybe you have seen 2.2 ohms or 22.2 ohms, these sort of values, but exactly 2 ohms or 20 ohms, maybe you haven't seen these values of the resistances. Maybe due to the physical property of the material, it is difficult to manufacture uh, exactly these amounts. So as the requirement of the binary weighted DAC is that the values has to be in equal proportion and also quite accurate. So this challenging task causes the manufacturing cost to increase. So this, with the increase of the number of bits, the expense tends to increase. So that can be termed as one of the disadvantages as well. And the third point states that uh, this particular design requires low switch resistances in transistors, because although a simplified switch is shown over here, but in practical applications, when uh, a feasible design has to be made, the switches is supposed to be made using BJTs or MOSFETs. So those are supposed to have some internal resistances. So those internal resistances of the switches has to be as low as possible, because for example, this branch twice R, there is a switch for R, another switch is connected, and so on. Let me consider these two branches. If we don't consider the resistances of the switches, let's say they are delta R and delta R. If we don't consider the values of these switch resistances, the ratio between these two resistances will give you 1:2. However, when the switching resistances are considered, the ratio will be close to 1:2 or 0.5, but it will deviate. It will not be equal to 0.5. It is supposed to deviate a bit depending upon the value of the switching resistance. So this switching resistance has to be as low as possible so that the ratio is almost equal to the value that is desired. So that is also sometimes difficult to maintain and can be termed as one of the disadvantages of this type of weighted resistor DAC.
Sir, I had some questions about the weighted DSC.
Yeah, okay.
Sir, the first question is from the amplifier we will get the inverted analog signal, right? As it is minus RF by R and something. So
Yeah.
shouldn't we give the reference voltage as negative potential so that we can get the actual analog signal?
Yes, you can do that. So you can either connect an inverter circuit along with the uh, reference voltage, or you can also connect it at the output side. So using an op amp you can do that. So if you set both the values of the resistances at the input side and the feedback side to be equal, then suppose you are getting a negative output voltage over here, that would be inverted and you will get the positive magnitude. Or you can also do the same task for the reference voltage. You invert the reference voltage first, then provide it to the rest of the circuit so that ultimately your output voltage is positive. So your assumption is, or your idea is absolutely right. So in order to avoid that, you need to change the polarity.
And sir, the second question is, as you said that we cannot get the accurate resistance as 2 twice R or 4R, and we cannot add extra resistances to make the weighted. Like if we add 1 ohm plus 1 ohm, the error will be higher, like plus del X plus del Y, as we have seen in the PMIT syllabus. So my question is, why don't we use variable resistors so we can adjust the resistance as we prefer?
Well, I haven't thought about that before, but maybe that would be a possible solution then. So uh, at this moment, I don't know exactly whether uh, it is, I mean, followed or not. In practical circuits, this method is followed or not. Variable resistances are used or not, or there is some drawback using the variable resistors. But it may be a possible solution because you can tune the values uh, according to your requirement. But maybe there could be slight variations in the variable resistor as well while varying the value. So maybe it is desired to have I mean steady resistances, because if variable resistances are used, maybe if you are not varying them intentionally, but for some reason they might get varied even if you don't notice. Okay, so maybe that could be one of the disadvantages. And most probably this sort of designs, maybe they come as a package. I mean sort of in the form of an IC or something like that. So maybe for that reason uh, variable resistances are not used, because they might also in what should I say, enlarge the size of the IC. Because if you're making the converter in an IC form, then all the things are supposed to be compact within like a package. So using potentiometers or variable resistances are supposed to increase the size of the device. So maybe that is uh, not used for that reason. But I haven't thought about it before, or I haven't studied about it before. Just as you are asking this question, from my intuition, I am just giving you an answer. It might not be accurate. Maybe you can also try to search for it, and I'll also try to look into this matter.
Okay, sir, I got it. You can proceed.
The second type of digital to analog converter circuit that I'm going to discuss here in today's lecture is R to R ladder uh, 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 digital to analog converter. So the name R to R comes from the fact that in this particular circuit, a ladder network is formed, as you can see over here, which only contains resistances of these two different values, R and twice R. So there are multiple resistances, but the values are having these two distinct values, the values of the resistances. So in all these vertical branches shown in this diagram, these contain a resistance of twice R, and in between these branches or in between these nodes, there are resistances connected with a value of R. So from the configuration of the ladder network and the values of the two resistances, the name of the converter is termed as the R to R ladder DA converter. And lastly, from the last node, twice R resistance is connected to the ground. Now, in weighted resistor, the purpose of having different valued resistances was to provide different weightage to the bits. So providing highest weightage to the NSB and the lowest weightage to the LSB. Here the task of the ladder network is going to be the same, to provide some means of giving higher weightage to the NSB and low minimum weightage to the LSB. So for this sort of designs, the branch which is connected closer to the op amp or the inverting terminal, that is termed as the MSB, and the branch which is farthest from the op amp, that is the LSB. So like before, these four vertical branches here are representing the four branches, 4 bits of the 4-bit converter. Suppose this is B1, B2, B3, B4. Similarly as before, whether the switch is connected to the ground or the switch is connected to the line of reference voltage, depending upon that, it can be considered whether a particular bit is set to 0 or it is set to 1. So if the switch is connected to VR, then it can be termed to be set to 1. Now, in order to have an expression of the output voltage or determine an expression for the output voltage for this type of circuit, it is useful to simplify this ladder network in terms of its Thevenin equivalent circuit. So then this whole portion of this ladder network is going to reduce into one single resistor and the voltage source. Then you can apply the concept of an inverting amplifier to determine the final output voltage V out. So for converting this whole network into its equivalent Thevenin network, we are going to consider each node at a time. So we are going to start with node A, then simplify this portion of the network, then jump to node B, simplify a little bit further in this way up to node D. So if we consider node A first, so for the first case, we are going to consider this portion of the ladder network. So from node A to ground, what are the elements that we have? We have a twice R resistor connected. Then we have another twice R resistor. And along with that, we may have a voltage source or may not have a voltage source available depending upon the position of the switch. So we can refer the voltage source to be B4 into VR. So B4 is representing the status of the switch, whether it is 1 or 0. And in this way, it is representing whether there will be the voltage VR available here or not. Now converting this portion into its Thevenin equivalent is quite straightforward. You have to eliminate the independent source first. Maybe as we are considering a voltage source, you can consider this branch, these two terminals of the voltage source to be short circuited. Calculate the parallel combination of these two resistances, which will give you the Thevenin resistance to be equal to R. And for the Thevenin voltage, what you can do, you can determine the voltage, an expression for the voltage drop across this twice R resistor. So uh, I mean, when you determine an expression for the voltage drop across A and 0, that will be equivalent to the Thevenin equivalent voltage for the branches up to node A. So for that, you can maybe consider a current flowing through this loop. So the expression of the current might be, you're going to have the expression to be V4 into VR, the sum of these two resistances 4R. Then for the Thevenin voltage, you can multiply this I into twice R, which will eventually give you V4 into VR divided by 2. So that is the Thevenin voltage that is written over here. So this portion of the network we can represent in terms of its Thevenin equivalent as shown over here. And for node B, we can consider this equivalent Thevenin representation from node A and proceed further. So if we go to node B, now we are going to consider this up to this portion of the network, up to this portion of the network, and this portion up to node A, it is going to be replaced with the series resistance and the corresponding Thevenin voltage, which was determined earlier. So once we do so, this would be our network up to node B. So here we have two different sources now. So in order to determine the Thevenin resistance, we can consider both the sources to be short circuited and determine the equivalent resistance from node B to ground, which is the series combination of these two resistances, then parallel combination of this twice R with this twice R. Eventually, again, we are going to get that the equivalent Thevenin resistance is equal to R. Now, for determining the Thevenin voltage, as there are two different sources, we can do that by applying the superposition theorem. We can consider one source to be active and another source to be short circuited. Try to find out the contribution due to that one particular source. Then for the second stage, we can consider the other source to be active and the previous one to be inactive. Try to do the same for the voltage between B and ground. So eventually that will actually give us this sort of an expression for the Thevenin voltage. So while you are considering one voltage source to be active, suppose you are considering this one to be active and this one to be inactive. So again, you can follow the same process of applying a KVL, try to find the voltage from node B to ground for this active voltage source. Then repeat the same, considering this one to be active and this one to be inactive, and sum the two contributions to get the final Thevenin voltage. In this way, we can further proceed up to node C, then up to node D. So in all, for all the cases, we'll see that ultimately our Thevenin resistance is always same. It would give us, for this particular configuration of R to our ladder network, for any node, the Thevenin voltage, Thevenin resistance is going to be remaining the same, which is equal to R. And the values of the Thevenin voltage is going to decrease proportionally, the contribution from each particular branch. So similarly, if we proceed up to node C, then node D, so finally at node D, this would be our final equivalent Thevenin representation of this whole network. So the Thevenin resistance will remain equal to R, but the voltage is gradually going to change. So in this process of change in the Thevenin voltage, you can see that the weightage to different bits are actually changing in multiple stages. So finally, at this point, you can say that we have, simplified this portion of the circuit. So at node D, we now have a resistor R and a voltage source, suppose VTH. Let me write it as VTH. So this is nothing but an inverting amplifier, you can say. So the output voltage would be minus RF by R into VTH, and the value of VTH is actually written over here. So you can replace the value of VTH, and finally, for this particular type of circuit, you'll actually going to be ending up with an expression of output voltage that is similar to the expression of the output voltage which was obtained for the weighted resistor DAC. So looking into this expression, you can again see that the weightage is given more on the MSB, and it is gradually decreasing with the smallest weightage to the LSB. So this configuration can also be used in place of uh, weighted resistor digital to analog converter, and some of the advantages are that only two different types of resistor values are necessary, R and twice R. You need multiple quantities of these two resistances, but only two variations of these resistances are sufficient. So using the same manufacturing technique, uh, multiple quantities of this resistance and multiple quantities of this resistance can be obtained. And whereas in case of the previous digital to analog converter circuit, it was a high requirement that the resistors had to be very precise and accurate. Now for this case, it is not. It is obviously better to have highly precise and accurate resistances, but even if there is some error, it will not significantly change the output of the DAC. And like I said, that only two different values of resistances are necessary, although multiple quantities of these two resistances will be needed. But the same manufacturing technique can be used to have multiple quantities of same valued resistances. So the manufacturing process becomes cheaper and easier. And the disadvantage of this particular circuit, which is quite obvious for having a ladder network and the number of branches which are supposed to increase with the number of bits. So the conversion process is supposed to be slower compared to the weighted resistor DAC. So that is the disadvantage of this particular type of DAC. So these were the two digital to analog converter circuits that I wanted to introduce in our class. Now, with that, I'd like to conclude our discussion on different types of analog to digital or digital to analog converters. So now, regarding today's lecture, If you have any question, then you can ask. Is there any question? Anyone wants to ask anything?
No, sir.
Okay, so let me conclude today's session then. Okay, one more thing. Tomorrow I won't be able to take your classes, so this week your class on the Thursday will not be held. Is it okay?
Yes, sir.
Sorry, I don't get you clear.